Always difficult in the beginning to be the first one. So let me start, Marc. There is something I could not get. Maybe you explain it, but I'm not really in the field. So what is the importance of the fractal inside of your design?
So mostly the fractal is you need to find a way here to reduce the footprint. So imagine the electric dipole response, the fact that the magnetic field it's normal to the plane that contains the electric dipole is here because of the distribution of current, right? And in MRI, if you want the structure to be efficient, as we saw in the HMA, you see you have efficiency that is usually close to the size where you are resonant with the frequency. And the frequency in MRI, you can't change. Like it's 7 Tesla, the frequency is 300 megahertz. So you can't say, oh, go to 3 gigahertz and I have a solution for you. That won't work. So if you want to change the size, you want your structure to still be resonant at the same frequency. And that's why we went into this fractal design, because the pattern, in fact, the small details of the pattern, I think, do not matter very much. But the fact that we are meandering this line to have this electric dipole behavior, but in a footprint that is much reduced, that's what we were looking for when we explored this fractal design. It's mostly just to have the antenna that is still working, but on a space that is much smaller. So that's mostly the use, because in this thing, especially in this work, there's only one element compared to the previous one. So we only use one resonance. There's no longer this idea of having like multiple resonance to interact to create some effect. Here it's really, I'm using the fundamental mode of the structure, and I want this mode to be around 300 megahertz, but the size should remain small, and how can I do it? So the problem is if you do just zigzag, for example, then you will lose this effect of the magnetic field, because one line compensates for the other, and in the end, you don't resonate much field. So you really have to find the pattern that is able to produce the polarization that you want. And this is why we modified in this slide, for example, we went from this kind of like split ring resonator to something that is slightly different, kind of like two split ring connected, but you change a bit the pattern of the currents, and that is helpful.
Thanks. More questions?
I ask you one question here related maybe to your robustness and of the external loading, something like that. And what is the working frequency? Your idea or concept only for a single frequency, or you can operate and the design for a wider frequency range?
So
I mean, at least for smaller, wider frequency.
No, of course. So that's what I tried to explain when I first answered to Moana. So the MRI comes with a certain value of magnetic field, and it is fixed. It's the engineer of Siemens or Philips that comes here, set it up, and you won't change. You can ask, but they won't answer. So what happens is, because of this, then if you do, the only thing is if you do proton imaging, you know the frequency, and then you have to make something that works for this frequency. Then the only moment where in MRI you can have multiple frequencies, and that happens, is that if you use other nuclei. So not only the hydrogen or the proton nuclei is used in MRI, you can use, actually people use a lot of sodium, carbon, and phosphorus imaging. But the problem is you don't usually do nice images because they are much less present than water in the body. So what you would do with this is you do kind of like spectroscopy, and you compare how much you do some peaks, and the height of the peak is the amount of sodium you have in the body. It's really just, I'm just saying like this. I mean, people are specialists of this, and they will kill me if they hear that. But just to give a perspective, you can follow metabolic processes with this. So that's really, really interesting. If you can measure phosphorus, you have this ATP molecule, and you can track how much ATP you have in the cells when you're doing exercise and stuff like this. So a lot of people, and actually MRI started with this idea of metabolic imaging first. So that's a moment where you can make structure that can be resonating at 300 megahertz, for example, for proton. And because the gyromagnetic ratio of each of these nuclei is different, then you have the phosphorus, it's probably 120 megahertz, the carbon is 60 megahertz, and so on and so forth. So you can have different frequencies if you use different nuclei. But for the really just the imaging in the most basic operation, most of the time it's the proton frequency, and that's the only one you care about. And we are talking, just to also give another perspective, this is interesting because, you know, a lot of time I was working on elastic and acoustic metamaterial before starting at Institut Fresnel. And you will see every time we'll ask, okay, what's the bandwidth of your metamaterial, right? Because every time you can make very nice metamaterial, but they work very, very nicely at just one frequency. And if you do communication, if you do things like this, you need huge bandwidth, and you don't have it most of the time with the metamaterial structure. But here, the good thing is MRI works at single frequency. Really, you know, the pulse we are sending, the MRI pulse, they are something like, I don't know, let's say 500 microsecond, 100 microsecond long, but the frequency is 300 megahertz. So you have 1,000 periods inside your pulse. So we still call it pulse, but it's almost like it's continuous wave excitation, in fact. So this is why I only show images at single frequency, and the structure is always at 300 megahertz, because in fact, the bandwidth that you need in MRI is just a few kilohertz around the central frequency that is in the hundreds of megahertz. So you don't really care about over frequency, only if you do single nuclei. As soon as you introduce more nuclei, then you have other parts of the spectrum to deal with.
Okay, thanks. This was my question here related to your.
No, it's a very good question.
Thank you. Okay.
Thank you. Do we have more questions?
I think I see a question in the chat. It appears, but I've lost it.
Any thoughts about low field, smaller than 1 Tesla applicability?
That's a very good question. So it will be different challenges, clearly. I think right now, in the last big radiology conference, Siemens put up like a 0.5 Tesla magnet. So, you know, they want to play both ends. You want to have scanners with extremely high magnetic field to do research and extremely performant imaging to look for, okay, what's the tiniest thing I can see, what's the fastest thing I can see. And if you talk to scientists in neurospin, they have tons of ideas on what is really hard to be seen today with the hospital grade scanners and what you can see if you had like stronger magnetic field. And that's why they are going into that direction. And on the other end, if you want to democratize MRI, you clearly want to have something that is less costly, because today, the rule of thumb is really approximately 1 million euros per Tesla. So it's quite expensive machine. And in fact, if you want to install this in third world countries or developing countries, the problem won't be not just like the upfront cost, but just the maintenance. Because as I said, the scanner is always on. So you have to keep it cold, you have to keep it powered. Any power outage is nightmare. So you want to be very careful with this. And with this low magnetic field application, it's very, very interesting for developing MRI contrast, I would say, because the imaging resolution, so now with let's say new approach like machine learning, and they can reconstruct higher resolution with low resolution image. So people put this forward to, let's say, reduce the constraints on the hardware because the software can compensate. So in terms of metamaterial, then B1 inhomogeneities at 10 megahertz won't be an issue, but you would use it, for example, if you want to compensate for loss of SNR, because if you have less magnetic field, the image will take more time, and if you have a coil that is more performant, then you can image faster. And I think that will still be a problem, not because people are not patient enough, but usually because if you say to someone you need to stand 15 minutes completely still, you know, it's really hard because sometimes somewhere we're gonna itch, and especially I've tried, you know, I've volunteered a few times to do experiments in the MRI. So when you're really focused and you want to have good results, so you can put on yourself this discipline to, okay, I don't want to move But if you imagine someone with back pain or stuff like this, and you ask them, please stay 15 minutes without moving, it's really hard, right? So there is a limit in time where it's not just comfort, it's really people will move eventually and it will mess up with the image. So that's some variables that you want also to gain, because otherwise the image won't be that easy to read for the doctor, which is always like the bottom line. If you can't do anything with the image, why bother?
Thank you, Marc. Do we have more questions?
No problem.
Let's give it a thermal twist. So what is the challenge regarding heat in this kind of MRI machine?
So in terms of heat, you want to manage the SAR. It's like you don't want basically SAR, which is related to electric field, gets absorbed in the tissue and temperature rise. And today we use this figure of merit, which is SAR. That's one way to calculate a threshold at which, let's say, it's dangerous, it's not dangerous. But the threshold is, for example, if the entire body increased by 1 degree. That's the threshold there. But you have to think that you eat somewhere and the blood circulates, so it will diffuse also the heat everywhere in the body. So it's really hard to evaluate, and especially because MRI, they can't map. I've shown you all the B1 maps that are maps of the magnetic field. So because magnetic field has an impact on spins, we can image it, but electric field has not. And so you're kind of blind. So what you need to do is you need to do simulation, you do experiment, you show that the B1 map you simulate and you measure are the same. And then you can say, okay, the electric field in my simulation is good. That's the only way. So that's a big challenge. If you can have a system that can image temperature or that can image electric field, and some people are going into that direction, it is extremely useful for the MRI community. That's because right now we use this kind of like indirect evaluation of temperature, and so in MCube I think, but this was more in the CEA, in the people that are developing this MRI sequence, they look at, okay, how can they extract this information about temperature? So that's really the most thing. But then in terms of temperature management, people, I guess, would prefer to reduce electric field than to reduce temperature itself. Otherwise, there is also, to go back into a bit acoustics, I didn't talk about it, but noise is also an issue, especially for pediatric patients, because the MRI is really loud. And so there are, I think, projects going around where they want to look at what can be done to reduce noise. But it is, to be honest, there is like it's good to do research on that, but at some point the interaction you need to have with the industrial, they design this thing that is extremely complex, and so if you say to them, look, I want to drill holes in the MRI, they won't be very happy, right? So you need to really, I think, convince them that you can do good result, and then probably they will follow. But so the proof of concept you can do, but it's really hard to make that step into something more with these MRI noise issues. But hopefully, they one day people will complain enough that they will have to deal with it. Because today people put earplugs, you have a kind of like a sound system, and you're good to go, but it's very loud.
Yeah, I have experienced an MRI myself last May for 45 minutes, and it's really uncomfortable. Yeah. This sound is horrible. And actually, Marc, could you comment on the fact that so people might dress this kind of torus with a meta surface, which is deeply sub-wavelengths for absorption of sound, no?
Of course. We have a project right now where we are just intending to really. So there are some work to be done, but the issue is also that the sound is this kind of like clack sound, very short with lots of frequency content, and so even if you are really deeply sub-wavelengths, we are talking like extremely high sound pressure level and extremely broad, because it's really noise. It's like when when you switch it's not the RF coil that gets switched on and off, but what's making is clack, 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 clack. So very, very diverse sound. So if it was like mono frequency as the RF, I'm pretty sure like acoustic metamaterial could be nice. But since it is very broad, it requires really like cutting edge metamaterial proofing clearly, because we are talking about very like maybe 2 or 3 decades of sound frequencies.
So this kind of click, it's like a shock wave. I mean,
so it's actually it depends. It's not. I don't think they reach the shock wave level. But to be honest, it's interesting because it's not generation of acoustic sound directly. You know, you don't have air, or it's not sparks or stuff like this.
Yeah.
It's really the system kind of moves a little bit, and it's the vibration that gets translated into sound and radiates into the room. And it's due to a specific part. I didn't went into details, but when you do images, you need to make the B0 kind of change from time to time, just with on, off like this. And you have a signal that's almost like a TTL, you know, like a square signal. And every time you have a ramp, either up or down, you have a coil with a magnet, and you switch the current inside, and it's like the Laplace, Lorentz force, I think people call it. And so that's what you hear, in fact, is when you just switch this voltage on and off, or -1, +1, you hear the system just clack, 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 just changing a little bit. And what you hear is just the beat at which the image is happening. So sometimes it's because it's very fast, sometimes clack, 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 because you have more time between the change. But it's not technically, it's really vibration that gets translated to sound. So, but I tell you, like they know, like industrial know this, and they are already, I guess, making lots of effort to reduce it, and it's still very loud. So it will be like a very technical challenge.
Thank you so much.
No problem.
That's all for me. Great explanation.
Thank you very much.
Sebastian, Mark, we have another question in the chat.
Yes.
And if you see it, I can read it. I understand that the problem is too hard to invert in the sense of a target field approach. Example, I want to concentrate all B1
yeah, I see the question.
to a small chosen region of FOV. Is it so?
Yeah, so that's exactly how I try to articulate the presentation. So with a single element, and you place it nearby, and you can increase the B1 somewhere. That's what we are able already to do this, and we have solution, even Mutliwave commercial solution to this, not based on metamaterial, but some electric pads. They are able to focus B1 very strongly in one part. But if you will, so again, in terms of research protocol, you see, for example, people that they want to focus on here, you know, the inner here, the image of the inner here, so they want to have just a tiny field of view. So you can improve in tiny parts, but the more general aspects want to have B1, you know, the more homogeneous everywhere, because when they put someone in the scan, they don't know what they will find, and so they want to be sure that they can see everywhere. And so this is why there is application where it's interesting to have this element to focus B1 somewhere, or it's you need to have it. Hello, Patrick. Thank you. I see Patrick in the chat. Thanks.
Okay, thanks a lot, Mark, for the nice presentation, and let me just check once again if there is any other question.
I think everything's okay.
If not,
then I thank you very much, Bogdan, for the invitation, and I'll be in touch.
Thank you very much. And
Thanks.
your presentation is saved, and it will be available online soon.
No problem. Thank you.
Thank you very much. Thank you all.
Bye, everyone.
Bye.
Bye-bye.